Yes, I'm here to tell you there are only two types of alkene addition reactions. There are only two types of alkene addition reactions. Now, I know what you're thinking. There's a list of reactions here on the board. That's a lot more than two reactions. And all of these reactions work for alkenes and alkynes, so this list is really twice as big. That's a lot more than two. Yes, I'm here to tell you there are only two types of alkene addition reactions. What I'm going to show you here is a study strategy. I'm not going to show you new information per se. This is a way to help you organize your reactions, help you prepare for your exams, help you figure out what reaction is going on when you look at a new practice problem. This is something that I kind of made up on my own. This is not something you'll probably find in any of your textbooks. It's just a way to help you organize your reactions and be the best OChemNinja that you can be. So what do I mean there are only two alkene addition reactions? Let me show you. All of our alkene addition reactions start with some kind of alkene as the start material. The only difference is what it is being reacted with, what the electrophile is. For one class of alkene addition reactions, we are reacting it with some kind of acidic hydrogen. We'll call it just generic HA. The alkene acts as a nucleophile. Markovnikov's rule says the least substituted side of that alkene is the nucleophile, and we kick out the leaving group. As there's in a video about Markovnikov's rule, I have a separate video on Markovnikov's rule down below. And we form the Markovnikov intermediate with A- as our leaving group. What happens here depends on exactly what A- is and what the reaction is. That's not important. But this is one kind of alkene addition reaction, where we attack something with an acidic proton. The other type of alkene addition reaction also starts with an alkene, but it has a different kind of electrophile. It has some kind of electrophile attached to some kind of leaving group, where the electrophile has its own lone pair of electrons. And this is the big differentiator between the two types of reaction. In one case, we're attacking an acidic proton. In the other case, we're attacking something with its own lone pair of electrons. We still kick out the leaving group, but here's where it's different. In these types of reactions, this lone pair of electrons on the electrophile bites back down on the would-be carbocation, on the position where the carbocation would be if it were a type 1 reaction. Instead of forming a full carbocation, the lone pair on the electrophile bites back down on where the carbocation would have formed, and we form a new intermediate, a cyclic intermediate, with the new electrophile. And we kick out the leaving group as leaving group. What happens here, again, depends on exactly which reagents we're using and what reaction we're doing, but these are the two types of alkene addition reactions. One where we attack an acidic proton to form a full carbocation, like Markovnikov's rule, and one where we attack an electrophile with its own lone pair of electrons, which bites back down on where the carbocation would have been to form some kind of cyclic intermediate. I call these types of reactions type 1 alkene addition reactions, and these type of reactions type 2 alkene addition reactions. Again, this is something I made up, but this is a way to organize your reactions. When you see a new practice problem, what are you supposed to do? One thing you can do is look at what the alkene is reacting with, decide if it's a type 1 or a type 2 reaction, and that tells you something about the mechanism. A type 1 mechanism will go through a full carbocation intermediate. A type 2 mechanism will go through some kind of cyclic intermediate, where the electrons bite back down on the growing carbocation. So what we can do then is we can take this long list of alkene addition reactions and we can sort them into two categories. We can sort them into type 1 alkene addition reactions and type 2 alkene addition reactions. The type 1 addition reactions are where we are attacking some kind of acidic proton as the electrophile to form a carbocation intermediate. The second type, type 2 reactions, attack some kind of electrophile with its own lone pair of electrons, where that electron bites back down to form a cyclic intermediate. These are really the only two types of alkene addition reactions in this course. There's a couple in the type 2 list that I want to highlight. They do follow the type 2 pattern, but they require a little bit of discussion. Let's look at the hydroboration reaction. We start with an alkene in the hydroboration reaction. We react with BH3, where the hydrogen is attached to the boron. The alkene still is the nucleophile. It still attacks the boron. That builds up too much electron density around boron. If you remember the mechanism for the hydroboration reaction, I have a separate video on that down below. The boron-hydrogen bond breaks, and hydrogen bites back down to form the bond with the carbon. It doesn't form a carbocation and doesn't form a cyclic intermediate either. We form a bond with hydrogen and a bond with boron. There's not a cyclic intermediate here, but there's also not a full carbocation. I classify this in a type 2 reaction category. There's no lone pair on bromine, but something is biting back down on the would-be carbocation. We are not attacking an acidic proton, we're attacking boron. We're not forming a carbocation intermediate, we're not forming a cyclic intermediate either, but we are forming a reaction where the electrophile kicks out a group that bites back down on the would-be carbocation to form our new intermediate. So hydroboration reactions I consider a type 2 mechanism, even though it doesn't totally fit with the pattern of other type 2 mechanisms. The other one I'll point out is the ozonolysis. In the ozonolysis reaction, we react the alkene with ozone, O3. The ozone has a double oxygen double bond and a single bond with an oxygen with a negative charge. The alkene still acts as a nucleophile, and it attacks the distal oxygen. That builds up too much electron density around oxygen. These electrons go on to the central oxygen, and it's the lone pairs on this terminal oxygen with the negative charge. These are the electrons that bite back down on the would-be carbocation. I have a separate video on ozonolysis down below. The intermediate here is a cyclic intermediate. It's not a 3-atom intermediate, it's a 5-atom intermediate, but it is still a cyclic intermediate. We still get the electrons biting back down on the carbocation. It's not from the same atom that was attacked, it's a separate oxygen, but we still get the cyclic intermediate from the electrons biting back down on the growing carbocation. The same is true for the dihydroxylation reaction. These are still type 2 reactions, even if it's not the same atom that does the biting back down on the growing carbocation. This is all you need to know. These are the 2 alkene addition reactions. As you start to study, as you go through these reactions, see if you can classify them as type 1 or type 2. When you get to a new practice problem, before you draw anything, see if you can identify it as a type 1 or type 2 reaction. By doing so, this is helpful because it tells you what kind of intermediate you're going to form, whether you're going to form a carbocation intermediate or whether you're going to form some kind of cyclic intermediate. There are only 2 alkene addition reactions.
Thanks for watching. The best way you can support this channel is to let your friends know about these videos, especially ones who go to different schools. Help spread the word around the country. As always, don't forget to like and subscribe.